Hi everyone, welcome to this new video, the first of 3 videos devoted to shuffle in Apache Spark, and I will start with the last choice, with the last chosen shuffle writer called SortShuffleWriter, and I will show you it in 4 different examples. In the first example, I will use a partial aggregation, which is represented here as tree reduce operation in the old RDD API. And later I will play a bit around this concept in three different applications. But before that, I would like to show you where everything starts. So the starting class is called SortShuffleManager. And as you can see, there are 2 different and quite important methods. The first method is the register shuffle, where Spark chooses what shuffle writer should be used. And as you can see here, for every scenario, it creates a shuffle handle object corresponding to the shuffle writer. And if you check where these objects are used, you can see that we have a method called getWriter, which does some pattern matching on these shuffle handles and returns a shuffle writer corresponding to it. So for our case, you will see that we will use the default, which will be created if these 2 conditions are false. So if we cannot use the bypass merge sort shuffle writer, and we cannot use the unsafe shuffle writer, which is reserved mostly to cryoserializer under some assumptions and to unsafe rows, so to Spark SQL. So let me start with the first code. So as usual, I added some breakpoints in the code to show you what happens under the hood. And I will start with the first example that will use SortShuffleWriter to perform some partial aggregation. So as you can see, we are here in the first check, verifying whether we could use bypass merge sort shuffle writer. And as you can see, since we are using a partial aggregation, so aggregation which is executed partially on the mappers and terminated on the reducers, we cannot use this shuffle mode. And as you can see, we are also using Java serializer, and this serializer doesn't support objects relocation, which is one of the criteria of the choice for serialized unsafe shuffle writer. So it will logically return false here, and as you can see, it's true. So automatically we can see that we will use the base shuffle handle and of course sort shuffle writer corresponding to it. So that it is happening right here, and everything starts by taking all the records for the mapper for the map task. And we'll just as you can see that we are using the shuffle map task, and we are adding them first to some external sorter that will perform, of course, the sorting, but that will also perform spilling that I will show you in the 4th example. And we are starting, so obviously we had a very small RDD, that's why we didn't spill anything to disk, which means that we can directly write and generate the shuffle files for this first mapper task. And I will try to retrieve the location of the file, which is this one. So as you can see, it's the block, Apache Spark's block manager, that will be responsible for writing the shuffle files in this location. And as you can see, the generation just happened because we have the data and index file for the map task. And Spark also called commit all partitions of one of available of the single available shuffle map output writer, that generates shuffle files on local file system, and which also not only and which confirms that the shuffle generation succeeded by creating this index file, indicating, by the way, where the reducers can find the data which they need to perform the reduce stage in the processing. So in our case, it will be the sample sum of two numbers. So now, if I'm not wrong, yes, it's still the first map. And now we should do the same operation for the second map, because if you check the code, I created the RDD with 10 partitions. So we should next do the same for the map ID 2. As you can see, it's correct. Map ID 3 as well. And all of them will generate the same files. So the index and the data containing the shuffle information. And let me skip this part because it will do exactly the same thing for the remaining 7 partitions. So in the second example, I will show you what happens if we have very few shuffle partitions. In occurrence, we have only 2, and we didn't modify the value of this configuration property, which is equal to 200, which corresponds to the default number of shuffle partitions. And in this test, you will see that we will use the bypass merge sorter, also because the group by key in RDD mode doesn't behave the same like in the dataset. So, but that's not the main reason for that. That's one of the reasons, because thanks to that, the map side combine is false. So we are not forced to use other SortShuffleWriter. And also the primary reason why we can use the bypass merge shuffle writer is that we have a very few shuffle partitions, which, as you can see, is equal to the number of shuffle partitions is equal to 2, whereas the bypass merge threshold is still 200. So that's the reason why later in the shuffle operation we will use bypass merge sort shuffle handle and bypass merge sort shuffle writer. So I will not continue in this example because it's not the goal of this demo. I will rather show you, or rather prove you, that SortShuffleWriter doesn't work with dataset API. So as you can see, I first modified few configuration properties, namely the number of shuffle partitions and also the bypass merge threshold you saw previously. And in this case, the condition I showed you before will be false, because if you remember, we compare the number of shuffle partitions, which for this demo will be 2, with the number of bypass merge threshold, which here will be 1, and this condition will be false. We will evaluate to false. But the main idea why we cannot use the SortShuffleWriter here is that the abstraction, the underlying abstraction used to represent data frames, that data sets on disk and on memory, supports objects relocation. So that's a concept that I will explain in the dedicated blog post to unsafe shuffle writer. But anyway, that's the reason here, and you will see this here, because as you can see, to operate on unsafe rows, we will use unsafe row serializer, which whose supports relocations of serialized objects method returns true, which means that we'll enter into this condition. Sorry, we will enter to the last else case, because all other conditions are also evaluated to true. And we will automatically use another shuffle handle and another shuffle writer. As previously, I will not continue since it's not the goal of this demo. And to terminate, I will show you the spilling. So the spilling happens when Apache under the hood Spark will use in-memory structures like in this case maps or buffers, arrays, and it will add every new map, every new record generated by the map stage to this structure. And if it cannot acquire more memory from the task memory manager, it will spill all so far accumulated entries to disk, so that it can make some more space to accept other records. So one of the conditions, so to simulate that, you can either have a very big data set with a lot of data in the map task, but it can be kind of slow to demonstrate, or you can also use a parameter which is called num elements for spill threshold, which will trigger spilling after putting this number to the in-memory shuffle structure. And for me it will be 500 since I'm using 2 partitions, and approximately a half of the data will be written to the spilling file. So let me demonstrate it. So first, of course, we are checking whether we can use the SortShuffleWriter, and now we can process the first map task by inserting all records to the sorter. And as you can see right now, we are verifying for every record. You can see that we are iterating over all records from the records input, and we are verifying every time whether or not we should do the spilling. And as I said, there is a sizing condition on the size of so far accumulated elements, but there is also another condition, which is the one involving the property I customized just in my code. So as you can see here, we read so far 501 elements, and as you remember, I put this value to 500, and that's the reason why we will write the data, the shuffle data on disk. And to show you that, I will go to my file system and show you that we are correctly generated one spill file, but only one, because for the second 500 elements we will stop, because the next 500 elements will be the last elements processed in this map task, and they will be combined with the shuffle file to generate. As you can see right now, we started to generate the shuffle file with the data for every partition, every shuffle partition, because as you can see, we are incrementing this number every time. So since we have 2 shuffle partitions, it should be done just now. You can see that we have the data file and the index file for the first map task. And now we will do the same for the map task number 2. And as you can see, that the temporary shuffle spilling file was removed for the first map task, and a new one was created for the second map. And we will do exactly the same thing to generate data and index files. And at the end, we will of course Spark will, of course, will perform some cleanup on the generated data by the block manager. So it was the first of 3 videos demonstrating some internals of SortShuffleWriters. And if you want to dig a bit more this topic, I put the link to the article in the description of this video. It was Bartosz Konieczny from waitingforcode.com. Thanks for watching.